Hello, this is the final presentation of our retractable cool cover by Ethan, Aaron, Alex, Nicholas, Aiden, Ethan, Brandon, and Kaya. And this is Team 10. So the overview of what we're going to be showing you today. We have an introduction to our problem and how we're going to solve it. We have the problem definition defining what our problem is. We have the concept generation and selection going over um, how we approach this problem and different solutions we thought of. We're going to go over our final concept, so the final choice we made, the engineering analysis, going over how we analyzed our final concept based on our specifications. We have our concept prototyping, which is taking our prototype and how we iterated it to where we're at now. The budget analysis to taking our $800 budget, which we had for all eight of us, and seeing how we spent it and how we still have money to spend, and the conclusion finishing us off with some references. So today, the pool cover in the current market, it's they're automatic but very expensive. So it's not affordable for the everyday person. Some of them that are not automatic are much more affordable, but they don't have as much utility, and they're a pain to set up and not visually pleasing to look at. Um, some of these, or all of these pool covers are not meant to have load-bearing capacities. So that means no one could stand on it, no one could put furniture on it. It's basically a space where it can't be used. And also, some of these automatic pool covers require a complex installation process, which takes a lengthy process and sometimes installation teams to come out and do it. So, looking at some of the pool covers on the market, the first one we have on the left is an automatic pool cover, but as you can see, it's expensive with a price tag of $9,685, which also takes a installation team to come and install, which it also cannot support any load on it. So, we wanted to try to come up with something that it's similar to the idea, but that can take load, carrying capacity, and be affordable for the everyday citizen. So the middle idea is a manual pool cover. While it's still more affordable, um, it's not very appealing and it's not automatic. And again, it can't take any load. And the one on the right is probably the most common pool cover that everyone has nowadays. It's just a tarp, but like you said, takes a long deployment time to get there, doesn't look good, and it can't withstand any load.
After reviewing the current market, we saw that automatic pool cover systems are high in cost and do not offer any load capacity. In order to fill these gaps, we developed a project counter to create an affordable automated pool cover system that prevents debris from entering the pool while promoting functionality of the space. To define the success of fulfilling the project goal, 6 objectives were developed. These include affordability at retail price, limited required storage volume, maximized portability by limiting the overall weight, aesthetic appeal, ease of assembly and installation, and development or deployment/retraction time. The targets of these objectives are defined within constraints. These constraints are listed here as an area covered of 4 feet by 8 feet, an automated design that can be retracted or deployed in 20 seconds, a prototype budget of $800, can withstand a loaded 300-pound capacity, withstand extreme temperatures between 0 and 120 degrees Fahrenheit, safe to use with limited deformation with a load of 1 inch, properly sealed from debris as to limit the requirements on pool cleanliness, and then a time limit on developing a proper prototype of 2 semesters.
So we had a couple of different concept generations when coming up with a design. For concept one, we went with more a convertible car where it would have the same functionality of being able to retract itself, um, like in the same motion as a convertible car would. And that would be going from starting the automation from the beginning, from one end of the pool to the other end.
And then our second concept is basically um, a rolling cover with hinge slats that roll on two tracks on either side of the pool. So the cover, when retracted, would be stored in a roll inside a housing on one end of the pool. And then this design also has kind of an option to be cable assisted from the other end of the pool in order to maintain tension and kind of help ease the deployment process.
Another concept that Team 10 came up with to as a solution for the pool cover was to mimic the scissor lift mechanism, except it would extend horizontally instead of vertically. And so the way this would work is it would have the scissor lift truss system, and then it would also use a hydraulic to extend and retract it. And then to save on weight and cost, a polymer material would have to be used for the actual cover.
And the last idea we came up with was a hinge idea where it would basically mimic a door covering the actual pool. So the automation system would be powered by powered hinges. And then as you see in the picture on the bottom right, when it's fully deployed, it would cover the top of the pool. And then when it's retracted, it would be flush with the ground to the side of the pool.
So the next step here for Team 10 was to converge on the solution out of the four concepts that best fit our objectives. And so in order to do this, first we used an analytical hierarchy process or AHP table to weight our criteria based on their relative importance to each other. And then we used those weights and put them into a decision matrix table. And then we scored each of these concepts for each of the criteria, multiplied those scores by the weight, and then summed those weighted scores. So whichever design had the highest score in our decision matrix table would be the one that best fits our criteria. And the design that had the highest score was the rolling slat uh, concept with the rolling rails. So this general concept we decided upon, but it actually kind of was iterated until before we converged on our final solution that we ended up prototyping. So our original idea, we had a fully solid cover with consecutive hinges that were attached to each other, as seen in the first iteration CAD renderings in the top right. And then we started thinking about and doing more serious calculations on our cost and kind of manufacturability of this idea. So we ended up changing our requirement um, for the load bearing capacity to where we could allow for gaps in between our slats. And this would help a lot with our costs and our manufacturability. And so this is how we ended up with our second iteration where we have slats made out of wood and then they're connected by chains that'll take tension. And then over the entire thing, we have sort of a fabric mesh that's going to prevent the debris from getting in the pool. And then this design also implements a cable system where the cable is um, wound at both ends around the main spool, and then it runs around the rail on each side with a pulley at the very end. And this helps to just kind of maintain tension in the pool cover when deploying it, and then to help guide it along the rails and up to the spool when we're retracting it. So again, this kind of second iteration was our final concept, and this is what we are ultimately ending up prototyping. So here you can see in the retracted state, um, on the stand with the motor that we've chosen. We're only going to be using one motor as we believe this has enough torque to meet our 20-second deployment time. And then you can see the flow rails that we've chosen, which are basically the rails on the side of the pool with wheels, and then the cable system as well. So,
All right, and so in order to basically take on the load capacity that we set as one of our um, basically specifications for our pool cover, we ran a numerical analysis simulation through ANSYS, basically on the total deformation, equivalent stress, and the safety factor of our wooden slats that we chose as slats for our pool cover. So we're actually going with 2x6 slats as purchased, um, and with a 300-pound load as specified at the center of our slat, we saw a total maximum deformation of around 0.038 inches, which was within the bounds set within our specifications. Also, the stress wasn't enough to really damage the slats. As you see, our minimum safety factor at the maximum equivalent stress point was 3.27. And then as you can see within the diagrams, we have gradients for each of the deformation, equivalent stress, and the safety factor. Um, Additionally, we ran numerical analysis through ANSYS again on an eighth of an inch aircraft carrier cable that will be used to basically retract and deploy our pool cover. And so this was made out of pure steel. And as you can see, we ran a similar analysis where basically we put a force at each end of the aircraft cable and we saw a maximum deformation. It was very small, a minimum safety factor of 15 with the corresponding maximum equivalent stress of 1100 psi.
The time for the cover to wrap around the circumference was used to make sure that the cover is able to deploy or retract within the 20-second limit. A diameter of 12 inches results in a circumference of approximately 37 inches, and a rotation rate of 10 RPM was used.
So, along with the numerical analysis, we also performed a mathematical analysis for the maximum deflection of the wooden planks. And for simplicity, we did not include the cutouts of the on the bottom where it would meet the flow rails. And so, using the 5 foot length that we cut our planks to and the cross section of 1.5 inches tall by 5.5 inches wide, we used some MATLAB code to calculate the moment of inertia, and we used the Young's modulus for the corresponding wood that we used, and we were able to find a max deflection of about 0.619 inches. And we also used a 300-pound force at the very center of the wooden plank. And the reason that MATLAB code was used was because we were experimenting with different woods and therefore different values of Young's modulus. And then we also performed a mathematical analysis to see what are the requirements for the motor for this pool cover. So we needed a motor that would be able to overcome the weight of the pool cover, which is 250 pounds roughly. And so using that 250-pound weight and an estimated radius of the shaft of about half a foot, we were able to get 125 pound foot torque. And assuming 10 RPM, I was able to calculate that we need a motor with a power of about 1/4 of horsepower, about 0.25 horsepower.
All right, so once our group did both the mathematical and numerical analysis, we transitioned to concept prototyping. So we took into account a lot of different materials that we could use for our cover. But in conclusion, we came up that a wooden plank would be the best and most optimal to cover our pool surface. In between these wooden planks would be gaps filled with a mesh to help complete the surface as a whole, and also to help distribute the amount of weight across the cover. So the material we did choose was a Douglas fir 2x6 wooden slat, and just because that the wood would take um, less amount of force on the motor itself when we develop that. And then also for the design process, we then did a physical analysis of the wood boards, where we tested the true deflection of the boards. So in the images below here, we had um, we measured the distance of the boards from the ground and then applied a load with one of the teammates standing on top of the board in the middle of it. And then after we then measured the total deflection that the board had, which came out to be zero point 0.5 inches at the center of the board.
Here we have the material that we had purchased for our prototyping. We just have we also went down to the Chandler Center to do some modifications to our material, like our boards, for example. We have created grooves on all our slats in order for to be guided by the rails. And then we also have our slats and rails together in the pictures, as well as our close-ups of the rollers that we are using for this prototype. Then we have a video that demonstrates of how it goes, how the slats are moving along the rails. As you can see in the video that it is guided pretty fairly, and if we have more on, if we were to add more on them with the actual guides on there, it would move smoothly over it, so there'd be no issues with that sense. I mean, so when making this prototype, we had a couple issues. For example, we had just certain shipping material purchases that never came in on time, so we were able to finish a full prototype. And sometimes when we were rolling over the slats on the rails, they weren't consistently sliding over the rails smoothly, so we had to just make a couple adjustments, and we plan on um, adding more rollers to the slats or to the rails themselves, so they're able to be more smooth. And once we get more materials, we plan on adding the mesh material between the slats, as well as purchase our motors and materials for next semester, so we could start doing the supports and the housing. We want to manufacture supports for the housing and motors, and then we want to do testify and deliver our products.
So here's our budget analysis. In yellow is the items we already purchased, and white is the items we plan to purchase. Out of our budget, we currently spent $441. So we identified what we need to do. So we needed to make an automatic pool cover that's affordable and can carry weight. And then we brainstormed our ideas to meet these objectives. And then we found our best design. So we did our engineering analysis, mathematical analysis, and then we performed that to see what materials we needed. We then ordered our parts. We did our demonstration of our current stage of assembly. And then our budget analysis showed that our current cost of the project and how much is left to spend on our unordered parts. And these are our references.